1.5, solving quadratic equations and finding square roots. We have our roots here, the square root of 4. We all know the square root of 4 is 2. What does that picture look like? It's a 2 by 2 that has an area of 4. The square root of 4 is 2 times 2. There's 2 of them in there. Therefore, the answer is 2. The square root of 16 equals 4. We see the 4 by 4 with an area of 16. And again, the square root of 16 is 4 times 4. There's 2 of them in there. Therefore, the answer is 4. Remember that square roots are understood to have a 2 here. Anything higher than a 2, and we would have to note that it's higher than 2. So when I was saying that there's 2 of them in there, it's a square. And that's why I kept saying there was 2 of them in there. Therefore, the answer was 2. The square root of 7 is not a perfect square. What does that look like? We see that we have a 3 by 3, and we also have a 2 by 2. But only so much of the square is filled in. If I needed to find the square root of 7 without a calculator, I would say, well, what are the perfect squares before and after 7? I know that the square root of 4, which equals 2, comes before the square root of 7, and the square root of 9, which equals 3, comes after the square root of 7. So we're in between the whole numbers of 2 and 3. Am I closer to 2? Am I near the halfway mark where it would be 2.5? Or am I closer to 3? What you need to understand is that all the non-perfect squares are between here. The square root of 4, the square root of 5, the square root of 6, the square root of 7, the square root of 8. All of the irrational numbers are in between the perfect squares. I would say the square root of 7 is after 2.5 and before 3. I would say that it's about 2.7. I guess that it was about 2.7. The calculator says that it's 2.6. Again, I don't mind my students being a tenth off. If I'm really unsure, then I would just do 2.7 times 2.7, and that would tell me exactly what my answer would be. Next, we have a cube, the cube root of 64, which now is 3-dimensional. I know that means the cube root of 64 can be broken up into 4 times 4 is 16 times another 4 is 64. There are 3 4s being multiplied under here. Therefore, the answer is 4. When it's a cube root, I need 3 of the same number, and then I can take that out. Example 1, we have the product property. The square root of a times b can be written as the square root of a times the square root of b. If I am trying to simplify the square root of 18, I'm trying to find a perfect square that will work out evenly. I know that I can break this up into the square root of 2 times the square root of 9. The square root of 9 is a perfect square. We have the square root of 2 times the square root of 9 is 3. And then my final answer for the square root of 2 times 3 is 3 square roots of 2. You're just putting them next to each other to show that multiplication. The square root of 98. Well, now the number's getting larger. I may not know something. That is a perfect square that's in there. So I want to show you the technique for being able to break down numbers if they're not small enough for you to break down. This is called repeated division, upside down division bar. I'm looking for prime factors. It has to be prime factors that are on the outside here. Prime factors would usually be 2, 3, 5, 7. Those are all prime numbers. The larger prime that you can find, the faster it will break down. And let's see here. I know it's even, so 2 works. Does 3 work? 9 plus 8 is 17, and 3 cannot go into 17, so 3 will not go in evenly. It doesn't end in a 5, and I don't know anything. 7 times anything, that's 98. So I'm going to go with 2. I'm going to cut it in half. 2 goes into 9. 4 times for 8, carry the 1. 2 into 18 would be 9. Now I can see 49. And I know for sure that it would be 7 and 7. You have a prime number at the end here. You keep going until the number on bottom is also a prime number. So the square root of 98 breaks down into 49 times 2. So I could do the square root of 2 times the square root of 49, which equals 2 times the square root of 49 is square root of 2 times the square root of 49 is 7, and my final answer would be 7 square roots of 2. On the next example, we have the square root of 6 times the square root of 21. Well, I could multiply it back together, but why would I want to do that if I'm trying to break it all down? So I'm just going to continue breaking it down, and I'm going to put them under the same radican. We have 6 times 21, and I know that 6 can break down into 2 times 3, and 21 can break down into 3 times 7. Now I'm seeing that I have 2 3's in here, or 3 times 3 is 9. That's a perfect square. And so I would rewrite this as 2 times 7 is 14, so 14 times 9, which equals the square root of 14 times the square root of 9. The square root of 9 is 3, so that would be 3 square roots of 14. Now we have the quotient property. The square root of a divided by b is the same thing as the square root of a divided by the square root of b. So I'm going to break this up into the square root of 2 divided by the square root of 25. And now I can see that I have the square root of 2, and the square root of 25 is 5. Same thing here. I can do the square root of 9 divided by the square root of 64. The square root of 9 equals 3, and the square root of 64 equals 8. Now, if life were only that simple, we cannot leave square roots in the denominator. That's going to be a problem. So, what we need to have is we need to have a conjugate. If I have a plus the square root of b, then I also have a minus the square root of b. If I have a minus the square root of b, then I also have a plus the square root of b. They go together. Really can't have one without the other. On this problem right here, if I start by thinking about, I have the square root of 5 divided by the square root of 2. The square root of 2 is a non-perfect square. What could I multiply to this that would give me a perfect square? How much more do I need in the denominator to make it a perfect square? Well, if I have in the denominator the square root of b, then I'm going to multiply by the square root of b. So if I have the square root of 2, that means that I'm going to multiply by the square root of 2. But whatever I do to the denominator, I've got to do the same thing to the numerator. That way I'm not changing the value of the fraction. The square root of 2 divided by the square root of 2 is still just 1. So I'm multiplying by 1. All right, now if I put this together, the square root of 5 times the square root of 2 is the square root of 10. And then the square root of 2 times the square root of 2 is the square root of 4. And now we can see we have that perfect square. Therefore, our answer will be the square root of 10 over the square root of 4 equals 2. You cannot have square roots in the denominator. Now, what happens when I see something like 7 plus the square root of 2? Well, if I have a plus the square root of b, then I need to multiply by a minus the square root of b. I'm going to multiply by 7 minus the square root of 2. Whatever I do to the denominator, I've got to do the same thing to the numerator. What we have here then is 3 times 7 minus the square root of 2 over 7 plus the square root of 2 times 7 minus the square root of 2. Distributive property, 3 times 7 is 21. 3 times the negative square root of 2 is negative 3 square roots of 2. Can you make a conjecture about what's going to happen in the denominator? I have exactly the same thing, except a plus and minus sign. What do I expect to happen when I have this situation? We have 7 times 7 is 49. 7 times the negative square root of 2 is negative 7 square roots of 2. I'm just putting them next to each other to show that multiplication. The square root of 2 times 7 is positive 7 square roots of 2. And then the square root of 2 times the negative square root of 4 is the square root of 2 times the negative square root of 2 equals the negative square root of 4. And now I just need to simplify. Your prediction about what would happen here is I have the negative 7 square roots of 2 and positive 7 square roots of 2. Those would cancel. I need to simplify this square root. So now we have 21 minus 3 square roots of 2 divided by 49 minus the square root of 4 is 2. My final answer then would be 21 minus 3 square roots of 2 over 47. This would be called rationalizing the denominator. Let's try this again. Rationalizing the denominator. I have 7 minus the square root of 5. That means if I have a minus the square root of b, I'll be multiplying by a plus the square root of b. 7 plus the square root of 5. 7 plus the square root of 5. Negative 6 times 7 is negative 42. And then negative 6 times the square root of 5 is negative 6 square roots of 5. Again, we're just using the distributive property to multiply. And here we again, in the denominator, we have exactly the same thing except for a minus and plus sign. The inner term would be negative 7 square roots of 5, and the outer term would be positive 7 square roots of 5. We can see that we're not going to have a middle term. 7 times 7 is 49. And then negative square roots of 5 times the square root of 5 is negative square roots of 25. Simplify. Negative 42 minus 6 square roots of 5. And that would be 49 minus the square root of 25 is 5. So we have negative 42 minus 6 square roots of 5 divided by 49 minus 5 is 44. Are we finished? I have 3 terms, 1, 2, 3. Can it be reduced? Notice that you have all even numbers here. I can at least divide by 2 on all 3 terms. If you're going to reduce, you've got to be able to do it to all the terms that are there. I have 1 term, 2 terms, 3 terms, a total of 3. I am going to reduce by dividing by 2. That'd be negative 21, negative 3, and 22. So my final answer then would be negative 21 minus 3 square roots of 5 divided by 22. Example 4, solve. Again, when we're solving, we're thinking of PEMDAS backwards. Is there any adding and subtracting that can be undone? Yes. Subtract 4. We have 3x squared equals 37. Is there any multiplying and dividing that can be undone? Yes. Divide by 3. Divide by 3, and we get x squared equals 37 thirds. This is a degree 2. I expect 2 answers. Are there any exponents to be undone? Yes. What is the opposite of squaring? That would be square rooting. And when you square root, it is plus and minus for an answer. We get x equals plus and minus the square root of 37 thirds. I need to make sure that I'm not leaving a denominator here. This would be the square root of 37 divided by the square root of 3. What can I do to get this to be a perfect square? Well, I could multiply by 3 over 3. That gives me 9. So we have x equals plus or minus, let's see, 37 times 3. The square root of 9 is 3. Final answer. Here we go with example 5. What are the solutions? Is there any adding and subtracting that needs to be undone? I see adding here, but it is in the parentheses. So that would not be there until we get to parentheses. Is there any multiplying or dividing? Yes, I see I'm being multiplied by 1/5. So I am going to multiply by the reciprocal, 5. And that cancels, leaving x plus 3 squared equals 35. Is there any exponents to be undone? Yes. So we have square rooting both sides. Get plus or minus the square root of 35. So x plus 3 equals plus or minus the square root of 35. The last thing I need to do is subtract 3. X equals negative 3 plus or minus the square root of 35. All right, example 6. We have dropped objects. We're modeling a dropped object. When an object is dropped, its height h in feet above the ground after t seconds can be modeled by the function. We have h for the height above the ground. We have t for seconds, and then we have h of 0, which is the initial height, where h of o is the initial height in feet. The graph h equals negative 16t squared plus 200 represents the height of an object dropped from initial height of 200 feet. It's shown at the right. The model h equals negative 16t squared plus h of 0 assumes that the force of air resistance on an object is negligible. Also, this model works only on Earth. For planets with stronger or weaker gravity, different models are used. Science competition. For a science competition, students must design a container that prevents an egg from breaking when dropped from a height of 50 feet. How long does a container take to hit the ground? Well, we're going to start first with our formula. We have h equals negative 16 t squared plus h of 0. What information do we have? We have it's dropped from a height of 50 feet. That is going to be the initial height then, 0. And the height above the ground was 50 feet. How long does the container take? How long? That would be t. We're solving for t. All right. Shift the 50 over. Negative 50 equals negative 16 t squared. I did adding and subtracting, not multiplying, dividing. Divide by negative 16. We get t squared equals positive. Just going to leave it for now as unreduced. Let's say positive 50 divided by 16. We get t equals plus or minus the square root of 50 divided by 16. So it's asking how long it takes. I'm going to use my calculator so that I can tell exactly what the seconds are going to be, because this is not how it is for seconds. It's t seconds. Does this look like seconds? That's how you know you should be using your calculator, because you want it to look like seconds. So I would say plus or minus 1.8 seconds. Therefore, the container will fall for about 1.8 seconds before it hits the ground.